Now, let us look at another set of what I like to call knots in chemical kinetics. Let us start out by writing an hypothetical second order reaction. Now, what you must note is that the order of a reaction can only be determined experimentally and not by the reaction stoichiometry. However, I am telling you that this reaction is a second order reaction. Okay? Now, starting out, we can easily write that the rate of this process is equal to this one here, dt, which is now equal to increase in the concentration of product with time. And now remember in the last video, all right, we explained why there's a half here. The half placed here is just to allow these two expressions to be equated. Why is it that we needed a half to allow them to be equated? Well, if you think about it, in a given second, when two molecules of A are consumed, only one molecule of P is produced. And that is telling us that the consumption of A is running at twice the rate of formation of P. And so in order to have these two equating, we have to half the rate at which A is being consumed. Okay? All right. Now what we could do is to say then, is to go ahead, and what we are trying to do here is to derive what we call the integrated rate expression for a second order process is equal to K times A squared, right? Square, which means second order. Now we can go ahead and rearrange this expression a little bit, right? By multiplying by 2 dt. So this one here cancel with that one. The 2 also cancels away. We could carry the minus across 2 if we want. So let's multiply by minus 2 dt. So this minus sign will also cancel away. So this is what we will be left with. And we could also go here and divide by a squared. So this cancels away. So this is what we'll end up with at the end of the day. dA over a squared is equal to minus 2k dt. Alright, that is what we have. Now the next step would be to do our integration. Now let us integrate, and we'll integrate between limits of a initial amount to a at some time t, and then we can go over here, integrate. We'll put the 2 minus 2k in front of the integration sign, seeing that k is a constant at a given temperature. So from time equals 0 to time equal t. Sometimes down the line, t could be 10 seconds, 20 seconds, whatever. Okay? Okay. Now, after integration, I'm going to just go back up here to give myself some space. After integration, and I will just skip a little step, what we will end up with is the following. A matter of fact, I could just put, okay, let's put that step in, minus, all right, 1 over a, all right, and this was, I think this was supposed to be at, yes, let's just not leave these things out, all right, okay, between a t and a naught is equal to minus 2k kt, okay, minus 2kt. Now, when we separate this part here, we end up with, let's say, if these two are negative, then we could ignore the negative signs. So we end up with 1 over, let's say, A naught is equal to, let's say, 2kt. Remember I said, if this one is negative and it is equal to this side, which is also negative, then the positives are equal to each other, right? It is the same thing as saying that minus x is equal to minus y, which is the same thing as saying positive x is equal to positive y, right? Just to explain there, so you don't think that I am skipping over a step in an arbitrary manner. Okay, so this is what we have. So we could rearrange it a little bit. Hope you're not too confused by the mess on this slide. All right, AT is equal to, and we could take this part across the equal sign, so it becomes positive, right? So we end up with 1 A naught plus, right, 2 K T. Okay, now what is the significance of all this? This is the integrated rate expression for second order reactions, by the way. That's what it is, okay? All right, let's just tidy up this slide and write it back, and so we can discuss it. Okay, so it is 1 over AT is equal to 1 over A naught plus 2KT, if I'm remembering correctly. Okay, now imagine that you are given some values, concentration values for A, right, at different time intervals. Okay, I don't know, let's make up some numbers. Maybe let's say 2.4, 2.1, 1.8, 1.5. All right, and this is like 0 seconds, 5 seconds, 10 seconds, 15 seconds. Okay, what you could do is to put 1 over the A values, these are AT values, put 1 over these AT values, and this part then would become the Y value, and then you could plot that against the T time values, which would be the X. All right, clearly then this part would be our slope, and this part here would be the intercept. And clearly, if you look at the slope, 2k, it's a positive slope, right? It's a positive slope. So if you do a plot, you expect to get a line looking something like this. Okay? This is, of course, when you plot 1 over a t, and down here you plot time in seconds. Now your slope is 2k. So let's say after doing this plot, you get a slope of, I don't know, let's say 0.9. That 0.9 is equal to 2k. Clearly then, k is equal to 0.9 divided by 2. Okay? And that will give you your k value, your rate constant value. Okay? All right, let's just point out one other thing, such that this video is not too long. I don't want to bore you too much. There is such a thing as half-life for second order processes. And as described in the previous video, half-life is the time taken for the initial concentration of a species to fall to half, or to decrease by 50% if you want to put it like that. Now, half-life then could be written as T a half is equal to initial concentration divided by 2. All right, seeing that for second order reaction, the integrated rate expression is this one here. AT is equal to 1 over A naught plus 2k. All right, I believe that is correct. Now what we will do is just to take this one here, all right, and put it right there. and then this T1/2, we will take it. Where is the T? There should be a T here. Yes, we'll take it and put it there. Okay, let's see how that works out. Let's see how that works out. Okay, I'll start over here. So I'll put now 1 over A naught over 2, all right, is equal to 1 over A naught plus 2k T1/2. Okay, 1 over A naught over 2 is the same thing as basically 2 over A naught, right? I believe so. Is equal to 1 over A naught plus 2k T1/2. Now what I could do is just to bring one of these over the equal sign. I could probably bring this one over the equal sign. And so what we end up with is 2 over A naught, right, minus 1 over A naught, yes, is equal to 2k T1/2. Okay? Well, the denominators are the same. So all we have to do is to subtract the numerators, right? That's how fractions work. So we'll end up with 1 over A naught is equal to 2k T1/2. Okay? We're not finished yet. We're not finished yet. Okay? Still have some work to do. Alright. We just basically then needs to divide by 2k. Alright? 2k cancel here. And so what we're left with is that T1/2 is equal to 1 over A naught times 2k. Okay, that is the half-life for a second order process. All right, let's write it back up top and say some stuff about it. Let's write it back up top and say some stuff about it. I know the slide is a little bit crowded, so let's write it back. So it's T1/2, this is what we derived just now, is equal to A naught times 2k. And this is the half-life. This is how you calculate the half-life for a second order reaction. Now, what can you infer from this? Well, first thing, for a second order reaction, the half-life is not a constant. It is dependent on the initial concentration of the species. Okay? So if the initial concentration of the species is high, then the half-life will be smaller. They share an inverse relationship. Okay, so the half-life of a second order process is not a constant, but is dependent on the initial concentration of the species in question. All right, so that's one thing you want to take away from it. That is important. And the other thing is that they share an inverse relationship. As the concentration of the species under consideration increases, the half-life decreases. All right, that is something important. Another thing about second order reactions that I could point out to you that could be useful is that the rate of a second order process, of course, the rate law is given like this, A squared. What this tells you is that the rate is directly proportional to the square of the concentration of the species in question. What can you get from that? Okay, let me see if I can explain. Time in seconds. All right. Time, no, I should not put time. Not time, not time, not time. What was I thinking? I should actually put concentration, all right, in molar or moles per dm cube, right? And the rate. Now, when you do a plot of rate versus concentration, what you find is that you'll get a relationship which is like this. It's more parabolic, or some people say parabolic in nature. All right, so yeah, it's parabolic in nature. And what that means is that if you have a reaction, all right, a second order reaction, if you should double the concentration of the species in question, then the rate will basically quadruple. Okay, so if you double the rate, then if you double the concentration, I should say, sorry, the rate will quadruple. It's not like for a first order process where if you double the concentration of the species in question, then the rate will basically double as well. That is for first order. However, for second order, right, which is what we're discussing here, if you double the concentration of the species in question, then the rate of the process will quadruple. Okay, so that is something that you should pay attention to. Okay, all right. I think that is enough. In another video, I think we will discuss something else. So take care.